Think you know black holes? Think again. Black holes have fascinated scientists and the public alike for decades, often portrayed as mysterious cosmic monsters with infinitely dense centers called singularities. But what if everything we thought we knew about black holes, especially these singularities, was wrong? Recent breakthroughs in theoretical physics and quantum mechanics suggest that singularities, the heart of black holes, where gravity is thought to crush matter to infinite density, might not actually exist. Instead, new models propose a more complex and less paradoxical picture of what's really happening inside these cosmic giants. Today, we're diving deep into 10 mind-blowing facts that are reshaping our understanding of black holes and challenging long-held beliefs about the universe's most enigmatic objects. Black holes are not infinitely dense. For years, the textbook picture painted black holes as having a singularity, a tiny, infinitely dense point at their core where the laws of physics simply cease to exist. But infinite density creates huge logical and physical problems, essentially breaking down our current models. New theories suggest that instead of collapsing endlessly, the matter inside black holes may reach an incredibly dense but finite state. This could be due to exotic phases of matter or quantum forces pushing back against gravity's crushing force. Essentially, black holes might have a core rather than a point, meaning their interiors are not an impossible mathematical abstraction, but something physically plausible. This shift helps resolve paradoxes and aligns black holes better with the rest of physics. Quantum mechanics challenges the singularity concept. At the heart of this revolution is quantum mechanics, the science governing the very small. Traditional general relativity predicts singularities, but quantum theory introduces a new kind of pressure, or limit, preventing matter from compressing beyond a critical scale. Quantum gravity suggests spacetime is discrete, made of tiny units that resist infinite compression, effectively stopping the collapse before a singularity forms. This quantum resistance acts like a cosmic safety net that preserves the fabric of spacetime. This interplay between gravity and quantum effects reveals that black holes aren't just simple gravitational traps. They're complex quantum objects where space and time themselves behave differently. This insight forces physicists to rethink not just black holes, but the nature of reality itself. Hawking radiation and the evaporation of black holes. Stephen Hawking's discovery that black holes emit radiation, now called Hawking radiation, completely changed our view of black holes. Rather than being eternal cosmic prisons, black holes slowly lose mass over astronomical timescales and can eventually evaporate. This process conflicts with the classical notion of singularities, which are eternal and unchanging. If black holes eventually disappear, then their internal structure must be dynamic, not frozen in an impossible state of infinite density. Hawking radiation also raises profound questions about what happens to information swallowed by black holes, sparking the famous information paradox. The idea that black holes are leaky and evolving rather than permanent singularities is a game-changer in modern astrophysics. The firewall paradox, a challenge to classic black hole theory. One of the most controversial ideas challenging the old black hole picture is the firewall paradox. According to this hypothesis, the boundary at the event horizon isn't a gentle threshold, but a blazing wall of high-energy particles that incinerates anything crossing it. This contradicts Einstein's principle that falling into a black hole would be uneventful at the horizon. The firewall arises from attempts to reconcile quantum mechanics with gravity, suggesting that black holes have highly energetic surfaces rather than empty boundaries. If true, this completely alters how we understand black holes' interiors and questions the existence of singularities by proposing a radically different internal structure. While still debated, the firewall paradox highlights unresolved conflicts in fundamental physics. Black holes may have a fuzzball structure instead. String theory offers a compelling alternative to singularities called the fuzzball model. Instead of matter compressing into a single point, black holes are thought to be composed of tangled strings spread out across the area inside the event horizon. This means the black hole isn't a dark void hiding a singularity, but a complex quantum object with structure. The fuzzball replaces the singularity with a fuzzy, extended core that can store information and avoid paradoxes associated with infinite density. This model has the potential to solve many mysteries, including the information loss problem, by treating black holes as collections of microstates rather than monolithic objects. Fuzzballs paint a picture of black holes that's rich, textured, and far less paradoxical. The event horizon may not be a sharp boundary. The event horizon has long been seen as a clean boundary, marking the point of no return. However, recent research suggests it may be more like a fuzzy quantum surface where classical physics breaks down. This fuzziness means information could slowly escape or be encoded at the horizon, challenging the idea that black holes trap everything inside forever. It also means the boundary isn't a sharp, immutable line, but a dynamic zone influenced by quantum effects. This changes how we think about black holes' interactions with their surroundings and suggests they behave more like complex quantum systems than simple geometric objects. This idea helps solve information paradoxes and reveals black holes as active participants in cosmic information flow. Black holes might contain a wormhole instead of a singularity. Some of the most fascinating proposals in theoretical physics suggest black holes might not harbor crushing singularities, but instead contain wormholes, hypothetical tunnels linking distant points in spacetime. This concept emerges from certain solutions to Einstein's equations where black holes are connected to white holes or other regions of the universe. If true, black holes could act as gateways, not dead ends, allowing matter and information to pass through or emerge elsewhere. Though speculative and not yet supported by observational evidence, wormholes offer an elegant way to sidestep the singularity problem and open new possibilities for interstellar travel or communication. This radical idea challenges us to rethink black holes' cosmic roles entirely. Gravity's true nature could prevent singularities. Emerging quantum gravity theories like loop quantum gravity propose that gravity behaves very differently at the smallest scales than Einstein's classical description predicts. Instead of endlessly increasing, gravity may become repulsive at extremely small distances, creating a quantum bounce that prevents collapse into a singularity. This repulsive force acts like a cosmic cushion that stops matter from compressing infinitely. This means singularities are not physical objects, but signals that our classical understanding of gravity fails at microscopic scales. This breakthrough hints at a universe where space and time have a discrete structure, and gravity is fundamentally modified, replacing singularities with finite, stable cores inside black holes. Observations of black hole mergers provide clues. Thanks to the groundbreaking detection of gravitational waves from colliding black holes, we now have direct observational evidence about black hole properties that challenge classical ideas. These mergers produce ripples in space-time that carry information about black holes' mass, spin, and structure. Remarkably, the data so far fits better with quantum-compatible models that avoid singularities, suggesting black holes have finite cores and complex interior. Observations are providing constraints that help scientists discard outdated singularity models and refine new theories. This synergy between theory and observation is ushering in a new era where black holes become laboratories for testing the deepest laws of physics. If you found this fascinating, please like, subscribe, and share your thoughts or questions about black holes in the comments below. The cosmos is full of surprises, and together we can keep unraveling its secrets.